Let's quickly understand the problem. And hey, if you are here just for the code walkthrough, feel free to skip ahead, but for intuition, approach, and why this works, stick around. Alright, so let's tackle the binary search concept today. We are given a sorted array of integers and a target value. Our job is to return the index of the target if it exists or -1 if it doesn't. For example, if the array is 2, 4, 6, 9, 11 and 13 and the target is 9, the output should be 3 since 9 is at index 3. Now here's the intuition. Since the array is sorted, this is the perfect use case for binary search. The idea is to repeatedly divide the search space in half by checking the middle element. If the middle element equals the target, return its index. If the target is smaller, search in the left half. If it's larger, search in the right half. We keep narrowing down until we either find the target or the search space becomes empty. So why it is important? We'll be using this exact binary search idea in multiple important problems later, like searching in a rotated sorted array, finding the first bad version, or locating a peak element. So understand this pattern and remember it for those problems too. Alright, let's quickly walk through the code. We start by initializing two pointers, left at 0 and right at nums.length -1. Now we enter a while loop that runs as long as left is less than or equal to right. Inside the loop, we calculate the middle index using left plus right minus left by 2. Now this part is important. Instead of writing left plus right by 2, we use left plus right minus left by 2, even though both of them will give the exact same answer. So why do we do this? Because if left and right are both large values, adding them directly could cause an integer overflow in Java. For example, if left value is 2 with 9 zeros and right value is also 2 with 9 zeros, their sum would become 4 with 9 zeros, which exceeds the maximum value an int can hold. By subtracting first and then adding to left, we safely stay within the range. Now, if middle element matches our target, we just return its index. If the middle value is less than the target, we know the target can only exist in the right half. So we shift left to mid +1. Otherwise, the target must be in the left half. So we move right to mid -1. If we exit the loop without finding the target, it means it doesn't exist in the array. So we return -1. The time complexity here is O log of n. At each step in binary search, we cut the search space in half. We start with n elements. After one step, it is n by 2, then n by 4, then n by 8, and so on until we reach one element. Why 1? Because once we are left with a single element, there's nothing left to divide. It's either our target or it isn't. That's a stopping condition. Mathematically, the number of times you can divide n by 2 before reaching 1 is log based 2n. Since each step does a constant amount of work, that is a couple of comparisons and updates, that's why the total time complexity becomes O of log n. Make sure you are super comfortable with this concept because binary search isn't just a one-off problem. It's a building block for many other popular questions. Follow Code in 60 on Instagram and on YouTube for more quick coding breakdowns. And drop your next problem in the comment.